Problem number 1 and 2, we're testing the transformations. We're also taking this long equation and seeing if we can come up with the basic function, so the basic version of this equation. So notice that this is a transformation, this is a transformation as well. So without those transformations, what does the basic function look like? Once we establish what the basic function is, then we could easily establish what the degree is. And then we sort of just start to break down and analyze what exact transformations we have. All right, so I know this +4 and this -7, those are transformations. So without those transformations, the basic function is just x to the 6th power. The variable to the exponent I see. So the degree of this function is just the exponent of my basic, or just the exponent in general of my function. So the degree is 6. The transformations. So we have 4 total transformations. This is the order of the transformations. We have 1, 2, 3, 4. And I just want to say yes, no. And wherever I say yes, I want to describe exactly what that transformation is. Horizontal shift, what this does is it picks up my graph and either moves it to the left or right. So first of all, let me pull up Desmos real quick so you guys can see. So we have f of x is equal to x to the 6th power. Or let's just do this, x to the... All right, so this would be the basic function. Without transformations, let's see how these transformations apply. So horizontal shift happens when I have addition or subtraction happening inside parentheses to the x. So I look inside parentheses, I see addition of 4. With horizontal shifts, we have to think opposite. So that +4 does not mean that my graph is moving to the right 4. What does it mean? So if I were just to highlight that transformation, do you guys see how my graph was initially right here at the origin and it moved, I picked it up and moved it to the left 4 units. So that +4 actually means my graph is moving to the left 4 units. So I'm going to be kind of lazy. I'm just going to write left 4. Okay? But on your exams, you want to put left 4 units. And I would put it right here. Let's say I have a horizontal shift. And what it's doing is it's moving my graph to the left 4. It's moving my basic graph, x to the 6th power, to the left 4 units. Now, do I have any compression or scaling going on? Compression basically takes my basic function and it makes it wider. Scaling takes my basic function and makes it taller and skinnier, so it stretches it. We only have those scenarios when we multiply by a number other than -1. So for example, if I take the same function and let's say I do 2 times x plus 6, maybe a bigger number, so you guys can see a big, let's do 20. So that was my initial graph, right? When I multiply by 20 here, what happened? Basically, my graph got skinnier, and even though you can't really tell, it also stretched and got longer. Now let's see if when I multiply by half, oh, it got wider. You guys see that? It got slightly, let's do 1 over 20. Clearly wider. So it depends what I multiply by, but depending on what I multiply, notice I'm multiplying by a number like 1 over 20 is not 1, -1, and 20 itself is also not -1. So whenever you multiply by a number other than -1, because -1 is when I have reflection, when I multiply by a number other than -1, either outside parentheses or even inside parentheses as well next to the x, things happen to the x values. They either get wider or they get skinnier. Okay, so do I have any multiplication in my original function where I'm multiplying the x by like a 2x or a 3x or 1/2 or even inside or outside parentheses? No. Okay, so I don't see any multiplication happening. No numbers are next to each other or outside parentheses being multiplied, so I do not have compression or scaling in this case. Now, do I have reflection? Reflection is when I specifically multiply by a -1, either outside or inside parentheses. So do I have a scenario where I multiply by a negative and it looks like this or like this? Okay, I'm going to look at my function. I don't see any multiplication. This is -7, so this is not -7 here or negative x right here. So I do not have reflection in this case either. Again, no multiplication. No numbers are next to each other indicating multiplication. Now I have a vertical shift when I add or subtract outside parentheses. So going back here, that -7, what is it doing to my graph? So now let me actually fully graph the entire function. Do you guys see how first it was close to the origin without any transformations? Then with that +4 inside parentheses, I have a horizontal shift where my graph moves to the left 4 units. And on top of that, finally, I have a vertical shift that picks up my graph and also moves it down 7 units. So vertical shift, I don't have to think opposite. So that -7 quite literally means down 7. However, that +4 for horizontal shift means to the left 4, not the right. All right, so we're going to go through the same process, same breakdown for problem number 2. The basic function is just x to whatever power the equation goes to. I do not want to include the coefficient, that negative. I only include that negative when I ask for what the graph resembles, not the basic function. The basic function does not include a coefficient. It's just x to the n power. So what is n power? 5. So the degree of the function is 5. All right, so let's graph the basic and let's see how these transformations apply. So we have x to the 5th power. So this is my starting graph. And then now let's go through the order of transformations. Do I have a horizontal shift? Something that moves my graph to the left or right? Well, I have a horizontal shift if I have addition or subtraction inside parentheses. So I look inside parentheses right here, and I see -4. So this means that my graph is moving to the right 4 units. Let's confirm it on the graph. So I have x -4 inside parentheses. So I'm going to go ahead and write those parentheses as well. And it has moved my graph to the right 4 units. Now, do I have compression or scaling? Am I multiplying by a number other than -1? Well, I look at my function, I see a negative right here, and it's next to the set of parentheses, so that means that I have multiplication. But specifically, it wants a number other than -1. This is a multiplication by a negative, so that would be reflection. Other than this indication of multiplication, this is addition, so I have no multiplication by a number other than -1. So again, I do not have compression or scaling, so I write no or none. But like we just said, are we multiplying by a negative? Yes. All right, so which example do I have? Do I have this one where I'm multiplying by a negative outside parentheses or inside parentheses next to the x? I see a negative outside. This would be an example of a negative inside parentheses. So I do have reflection, and it happens to be reflection outside parentheses. So that means, so I have this scenario, so that means I have reflection over the x-axis. So this is when it folds hamburger over the x-axis. So I would say yes, and then I would write, yes, I have a flip or I have reflection over the x-axis. Why? Because I'm multiplying by a negative outside parentheses. So now let's see this come into action. This one is probably a little bit harder to see, but if you really break it down, this side right here is gonna hot dog flip down here where my scroller is going. And that would be a hamburger flip across the x-axis. This side is gonna hamburger at the same time that this one's moving down, this one is moving up because it's a flip. So this one is going down, this tail end is going down, this one's gonna flip up at the same time. Technically, there is reflection there over the x-axis. It just looks a little bit funky because the entire function is not on one side. So it's not like a x squared graph where I go like this and then I go like this and it flips perfectly. Why? Because you can clearly see that everything is on one half of the x-axis. But that is what's happening here. This part is going down. This one, however, is going up. So we have reflection over the x-axis. Now, do I have a vertical shift? I have a vertical shift when I add or subtract outside parentheses. So that plus 7, let's see what it does to my graph. After flipping it, after moving to the left, moving it to the right and then flipping. That plus 7 is finalizing it by moving it up 7 units. So again, notice it's right here on my x-axis. When I do plus 7, it moves up. So I do have on top of that, I have a vertical shift. All right, do you guys see the importance of the basic function? The basic is basically what we start off with, and then we go ahead and identify and apply those transformations one by one after establishing what the basic is. So that is an overview of problems 1 and 2. Okay, now I'm going to do problem number 5 on the actual document. Find a polynomial function. So whenever we say polynomial function, we're looking for something that is a polynomial function that is either in, oh, I see what I did there, in expanded form or factored form. So this would be the factored form whenever you see the sets of parentheses. Expanded, it just looks like a long, kind of like this. This would be expanded. Do I see any parentheses? No. Do I see a long line of variables in descending exponential order? So look, it goes x to the 4th, x to the 3rd, x squared. So this would be an example of expanded form. And notice first it asks for the factors, so it asks for the sets of parentheses, then for us to basically multiply out the factors. So let's get some practice with this. So we want to find the polynomial function. We want to find this and this with real coefficients having a degree of 3. So the total degree has to equal 3. Okay, and then it lists the real zeros for me. So I'm going to go ahead and type them as I see them. I have -1 is real 0, so I'm going to write this as x equals -1. Then I have x equals 2. And then I have x equals 3. And it wants me to write this not with a coefficient. This is another version. Just like this. Sorry, I apologize. Okay, so this is all it's asking for. Here, I'll actually copy down exactly what the problem says for problem 5. This is kind of another version. Here. Okay, this is the exact problem. Find a polynomial function with real coefficients having a degree of 3 whose real zeros are -1, 2, and 3. So same thing applies. Degree is 3. These are my zeros. How would I write each factor as a 0? X plus or minus 1. So if R is a real 0, then X minus R is a factor of that 0. Let's do this one first. If 2 is a real 0, so if 2 is r, then x minus 2, x minus r is the factor. If 3 is a 0, x minus 3 is a real 0. If negative 1 is a 0, then x minus negative 1 is a factor. How could I simplify minus a negative? Well, I could just write plus. So that's why a shortcut that I mentioned in class is just write the opposite sign. So notice 2, I have minus 2 is the factor. 3 minus 3 is a factor. Negative 1 plus 1 is a factor. Or you could stick to the little formula we have, r and x minus r. That also helps. Now, what is the multiplicity? The multiplicity is the exponent, the number up top right here in the corner. I can't really point to it, but you see where my my little scroller is? It would be the number, the exponent of the factor. So this set of parentheses to what power? Well, I don't know the multiplicity exactly, but I do know the total degree is 3. So another thing I know about multiplicity is that the multiplicities add up to the total degree. So I'm going to write that right here. Multiplicities add up to the total degree. Okay, so if I know the degree is 3, each of these boxes somehow has to add up to 3. So the only possible way that the multiplicities add up to 3 is that if each box is 1, 1, 1. Make sense? So if I have 3 zeros, then that's the only way that they're going to add up. Finally, I establish, okay, what's the multiplicity? Okay, the multiplicity is 1. Is that an odd or even number? These are all odd, so I'm going to write O. Okay, 1 is an odd multiplicity. And this helps when we get to the graphing portion, but I don't think this question is requiring us to graph anything. It's just asking us to list the zeros. So if I were to list the zeros, I'd say, okay, the zeros are x equals negative 1, x equals 2, and x equals 3, just like how I see them. How would I write the factors? Well, I would copy down the factors I have. So x plus 1, then I have x minus 2, and then I have x minus 3. Now it gets to this portion where I have to expand this. So let me copy this and let's go ahead and practice expanding. Here you can clearly see what I mean by multiplicity. So sometimes, let's say my multiplicity is 2. So I would write x plus 1 squared. But for each of these, the multiplicity is 1. Whenever I have something to the first power, I don't necessarily have to write the 1, but it's still a good habit to remind myself, hey, the multiplicity actually means something. What does it mean? It's the exponent of your factor. All right, so now let's get to the practicing of multiplying factors. So I have x plus 1. I like to pick 2 first and then worry about the x minus 3 later. And then basically this is practicing distributing, and you take turns distributing. So since this is my first factor, all the terms, how many terms do I have? 1, 2, have to be distributed fully to all the terms in the second set of parentheses or in the other factor. So I have 2 terms. Each of these terms are going to be distributed to all the terms in the second factor. So I have x times x, which is x squared. Then I have x times negative 2, which is negative 2x. Okay, so again, I've distributed this term to every term in the second set of parentheses. So I'm done with the x. Now I move on to 1 because that is the other term in this first set. I multiply 1 times x, so I have 1 times x is 1x, so I'm just going to write x. And 1 times negative 2, which is negative 2. Okay, so basically, x plus 1 times x minus 2 is equal to x squared minus 2x plus x minus 2. I see a set of like terms, negative 2x plus x, I can combine. So I'm going to combine them. I have like terms. Both of them have x to the first power, right? So they're like terms. I can't combine x and x squared because this has a power 2, this has a power 1. So they're not like terms. Negative 2x plus x is negative x. Right? Negative 2 plus 1 is negative 1. Minus 2. So again, this is still the answer or the result of x plus 1 times x minus 2. I still have to multiply by x minus 3. So I'm going to go ahead and multiply. And after this, I will be done because every factor has been multiplied. So now, look how many terms I have to distribute. 1, 2, 3. Again, every term in your first set of parentheses, in this case I just had 1, 2. Every term in your first set of parentheses has to basically take turns being distributed fully to every term in the second set of parentheses. So, starting with x squared, I'm going to multiply x squared by x. So I have x cubed. Then I have x squared times negative 3. So that's negative 3x squared. Now, this one's done being fully distributed to every term in the second set of parentheses. So I'm done with x squared. Now I'm going to move on to negative x. Negative x times x is negative x squared. And negative x times negative 3 is positive 3x. Finally, I have negative 2. Negative 2 times x is negative 2x. And negative 2 times negative 3 is plus 6. I see a few scenarios of like terms. So I see x squared here and x squared here. So I'm going to combine these two terms. And over here I see x and x. So again, I'm going to combine these two terms because they are like terms. So I have x cubed alone. Has no like terms, so it stays x cubed. But then I have negative 3x squared minus x squared, so that totals to negative 4x squared. Again, combining those like terms. 3x minus 2x is just x. And then again, 6 doesn't have any like terms, so it's just 6. So the fully expanded form, believe it or not, this right here, this is the expanded form, the long version of this. So these are both equal to each other. Just one is in factored form where we have sets of parentheses, and the other is in expanded form. Remember, in class we went over how these are transferable. We can go from one to the other. And that is what it's testing you to do, to understand the difference between expanded and factor form. It's easiest to go from the zeros to factor form because we can then write, again, if r is 0, x minus r would be the factor. So automatically we have the factors if we have the zeros. The only thing that takes maybe a little bit of time is expanding. Problem number 8 is very similar to problem number 5. But notice we have a 0 that is a complex 0. So in order to understand that, I want to give you some examples again, and these are the examples we did in class. They're basically like little warm-up problems. What I want you to understand is that complex numbers always come in pairs. So if I have 3i is a 0, x equals 3i is 1, 0, that automatically means that x equals negative 3i is another 0. They always come in pairs. If they're telling me x equals negative 5i is a 0, then again, the opposite sign version, so if this is already a negative 5i, then x equals 5i also exists as a 0. So they always come in pairs. They're called conjugates. And these conjugates have basically a positive and negative version complex. And to prove this to you, I gave you like these two little mini formulas that are basically shortcuts to the square root property. So I'm going to write that. Let's see where I have space. Shortcut square root property. Okay, so this is a nice little shortcut that we can go off of. And just to prove it to you, let's say we have x squared minus 9. Let's do the full square root property, which says, okay, set it equal to 0. Once you have it set equal to 0, you see you have 2 terms, right? X squared and negative 9. I'm going to try to solve for x. So I'm going to add 9 to both sides. Now I have x squared is equal to 9. Okay, now here's where square root property comes in. I take the square root to both sides. And whenever I am the one putting the square root, I have to remember, okay, that means that I have the positive and negative version of square root 9, which in this case is 3. It's a perfect square. Not always is it a perfect square, but in this case, since I'm subtracting by a perfect square, I have x is equal to plus and minus 9. Plus and minus 3. So this is me actually doing the work. If I use the shortcut, I notice I have which version, x squared minus a or x squared plus a. Well, let me look at my problem, my starting off problem. I started off with x squared minus 9. So that means I have x squared minus a number, right? So if I use the formula, it's saying, okay, I have x squared minus 9. So that means right away I can conclude this, that x is equal to plus and minus square root 9. So isn't that what we already initially had? And then it's the same thing, just without that extra step of solving for it. All right, so whenever we see this setup, we can already conclude that x equals 3 and negative 3. However, what's important is that you understand that these are the zeros, right? These are the factors. And just like we do in the chart that we use, all right, so I identified the zeros from those factors. How would I write these factors? How would I write these zeros as factors? X minus 3. So if r is a 0, x minus r is a 0. So this would be the factor of this 0. The factor of this 0 would be x plus 3. All right, so that's important. That we have to understand, okay, this is the fact. Even though I was able to get to the 0 first before the factor, I also understand how to get the factor. And that applies for the the quadratic formula as well. When we have x is equal to, in that really big formula, negative b plus or minus the square root of b squared over 4ac, we get the x value solutions. But once we have the x values, can you find the factors? That's important because notice in this problem, they're going to ask us for the factored form, okay? And then also similarly, what if I have x squared plus 9? That looks a little bit different. Okay, if I do the square root property and solve for x, so now I have x squared is equal to negative 9. Take the square root to both sides. I have a negative inside the square root. So same thing applies. Because I took the square root, I have x is equal to plus and minus. But now I have a negative 9 inside my root. Since I have a negative 9, I have to be able to simplify this. What does this simplify? Right away, I like to take out the negative 1. So negative 1 times what is negative 9? Oh, well, negative 1 times 9. And this automatically, I know simplifies to I, and then I could just worry about the square root of 9 alone. So now I have x is equal to the plus and minus of square root 9 times I, and then I see that the square root of 9 is a perfect square, so I have x is equal to the plus and minus of 3i. Okay, so that means I have 3i, and I also have negative 3i. So this is what I was talking about, that the complex numbers always come in pairs, positive and negative. So how would I write these as factors? These are the zeros. The factor of the 0 is x minus 3i. And the factor of this 0 is x plus 3i. If I multiply these factors together, what do I get? All right, so before we answer this question, I don't want to confuse you. Let's go back over here. Again, we have x is equal to 3 and x equals negative 3. The factors are x minus 3 and x plus 3. These are the factors of this right here, x squared minus 9. That is important because I've asked in class, how do I know I'm done factoring? I know I'm done factoring when x is raised to the first power. So because I see an x squared, that means I have two factors that I could split this into. So x squared minus 9 is not fully factored. If I want to find the factors, those factors are x plus 3 and x minus 3. And I can prove it to you right now. This is technically the expanded version, and this is the factored version. How do I know? Well, let's do the math. X times x is, whenever we multiply it out, we get the expanded version. X times x is x squared. X times negative 3 is negative 3x. 3 times x is 3x. And 3 times negative 3 is negative 9. Notice these are like terms that cancel out. Negative 3x plus 3x is 0, so I have x squared minus 9. The expanded form. These are the factors of the expanded form. So, understand that I'm done factoring when every x value is raised to the first power. So let's say I have the factors like this, and I ask you to multiply this out. So without hesitation, what is the multiplication of these two factors? The expanded form. X squared plus 9. What is the expanded form of... Oh, why did all of it erase? That's not good. I just want to erase this. What is the expanded form of x minus 5i times x plus 5i? Or what is the expanded form of x plus 5 times x minus 5? It's x squared minus 25. Since I see an I here, it would be plus 25. So that's the difference between these two. They basically have the same factors, just one has an I attached to it. If I see the plus, x squared plus a number, as opposed to x squared minus a number. Same factors, just one has an I for the same reasons that, look, this is x plus 3i, x minus 3i, Over here we have x plus 3, x minus 3. The only difference is that I have x squared minus 9. So minus 9 gives me these like clean factors without an I. X squared plus 9 gives me factors that have i's. So keeping that in mind, let's try to solve problem number 8, which is, again, very similar to problem number 5. Find a polynomial function of degree 3. So again, we know the total degree is 3, whose zeros are -4 and 3i. So right away, I know the zero is x equals -4 and x equals 3i. And because I see it's a complex, I already know in the back of my head that complex numbers come in pairs. So without telling me, it's implied that -3i exists, and it's also a factor. I also included this column right here. Is it an x-intercept? Well, as long as the zero is a real zero, because these are all zeros. X equals 4, x equals 3i, x equals -3i, but not all of them are real zeros. So do I have an x-intercept? Well, I know x equals -4 is a real number, so it's real. So do I have an x-intercept? Yes. The answer is yes. I have an x-intercept at -4, 0. So I have a point on the x-axis. Is this a real zero? No. How do I know? Because of the I. So because that, I do not have a point. So I'm going to write does not exist. Or I'm just going to write not real. So this is not something that I could write as a point. If I do write it as a point, is 3i a point? No, I can't. I cannot possibly graph an imaginary number. So not real, not real. So I have a not real zero, automatically not an x-intercept. But we can still follow through with this problem and write all the factors. So the factor for x equals -4, if r, -4 is a real number, then the factor is x minus r. So in this case, x plus 4. X equals 3i, so x minus 3i. X equals -3i, so x plus 3i. Okay, so these are the factors. Well, again, I don't know the multiplicity, but I know they have to total up to 3. So if I have 3 zeros, they all have to add up to 3 somehow. So each multiplicity, each factor is raised to the first power. All these are odd. One is odd, one is odd, one is odd again. So that means cross. Ooh, I'm not going to write cross here. I just caught my mistake. This is the only point that exists on the x-axis. Since this does not exist on the x-axis, it doesn't cross or bounce on the graph. All right, because it's not on the graph. So there's no way that my graph is going to cross or bounce off a point if the point does not exist. So now where do I write my factors? So what are the zeros? I would say my zeros are x equals -4, x equals 3i, x equals -3i. These are all my zeros. What are my real zeros? Just x equals -4. But all my zeros are x equals -4, 3i, and -3i. So let me go ahead and write the factored form. X plus 4, x minus 3i, x plus 3i. And then look, it's saying write the final answer in exponent in expanded form. So that means multiply everything out. So whenever I multiply something out, I like to start with the first two. But in this case, since I see a complex factor multiplied by another complex factor, this is kind of going into what we just practiced. Doesn't it simplify to x squared plus 9? The factors of x squared plus 9 are x minus 3i and x plus 3i. These are the factors of x squared plus 9. So if I'm looking to multiply these factors out, I should get x squared plus 9. And I still have to multiply this by x plus 4. So right now, all I did was simplify this. I still have to multiply this by x plus 4. So then I distribute x times x squared is x cubed. X times 9 is 9x. 4 times x squared is 4x squared. And 4 times 9 is 36. I see no like terms. I just have to write them in order. Right now, it's not in a descending exponential order. I have x cubed, then it jumps to 9x, and then it jumps to 9x squared. So I just had to switch these two so that it can be in proper standard form, which is descending exponents, variable exponents getting lower. And this would be the final expanded answer. The important thing here is that you know how to identify that zeros have come in pairs. You know how to write the zeros as factors, and that you know that these complex factors, when you multiply them, they multiply out to something like this. Now we're going to do problem number 3, where we're practicing being able to use this new chart where we determine the end behaviors. So in order to determine the end behaviors, we have to establish what is the leading term of the function. So what is the term with the highest exponent? And looking at the leading term, we're looking at the coefficient, the number in front of the variable. So for example, if the leading term is 3x squared, 3 would be the coefficient. And we're determining whether this coefficient is positive or negative. And also looking at the leading term, we're looking at the exponent of the leading term, which will be the degree. And we're also establishing whether this degree or this exponent is even or odd. And this will determine what the graph looks like from start to finish. So these are called the end behaviors. How is the graph behaving when it begins and when it ends? Okay, so we're going to be reflecting and going back to this chart. And looking at problem number 3 to get an idea. Again, the whole point of doing this is to get an idea of what the graph looks like without actually graphing it. We're comparing all the terms in the polynomial, which one has the highest power exponent. So I look here, I have x to the 4th, x cubed, x squared, x to the 1st, and x to the 0. X to 0 is just 1, so we never write x to 0 because it equals 1, so this is like saying 50 times 1. Not really necessary to write x to 0 power, but if we're comparing all these terms, I have 1 term, 2 terms, 3 terms, 4 terms, 5 terms, comparing all the terms, which one has the highest power exponent? Obviously x to the 4th, and this one actually happens to go from descending order for the exponent, so it goes from highest to lowest, which means that this polynomial is already in standard form. So it's very obvious what the leading term is, and that term is x to the 4th power. Okay, so the degree is just the exponent itself. So 4 is my degree of my leading term, the exponent of my leading term. And it's safe to say that 4 is an even number. So right now I know that my leading term has an even degree. That's important when we look at our chart. Also looking at my leading term, what is the coefficient? So the number in front of my term. I don't see a number, but that number, it's not like 23x squared where obviously the coefficient is 23. If I don't see a number in front of x to the 4th power, that number is 1. So my coefficient, is it positive or negative? It is positive. So now what I want to do is I want to look at my chart of end behaviors. And I know I have a leading coefficient that is positive, so I'm looking at this column. And I have a degree that is even, so I'm looking at this row. So what should my end behaviors look like? I have an up-up scenario. Do you guys see that? Positive and even. My end behaviors are up-up. So this graph, even though I have no idea what it looks like, at the very least, I know it starts up and ends up. The next thing it asks is for the number of turns. The number of turns is equal to the degree. So I'm going to write degree minus 1. So if my degree is 4, that means I have 3 turns. So if this is how my graph starts and finishes, in between, I'm going to have 3 turns. 1, 2, 3. So that's going to be a total of hills, a combination of hills or valleys. Turns always look like these guys. So that also gives me a rough idea of what my graph looks like. And that is all. All right, so that's just us practicing the chart. We're going to do the same thing for all of these guys, basically. All right, so we're going to do the same thing for this problem right here. F of x is equal to x to the 5th power. So leading term, this one is a no-brainer because how many terms do I see? Just one. So obviously that's my leading term. So I'm just going to put an arrow. That's my leading term, obviously, right here. What's the degree? 5. Now this time I have an odd degree. And then the number in front of x to the 5th power is -1. So that's obviously a negative coefficient. I can do the number of turns right now, 5 minus 1, which is equal to 4 turns. So let me look, using these two sets of information about the leading term, I should know what the graph looks like. So now my coefficient is negative and my degree is odd. So negative and odd, I have an up, down, and behavior scenario. So I know my graph starts like this and ends like this, and in between is the number of turns. I should have 4 turns. 1, 2, 3, 4, and we can count them. That's one valley, that's one hill, that's another valley, that's another hill. That's total combination of hills and valleys, 4. Leading term is obviously this. There's no other terms to compare it to. So if that's the only term, that means it's a term with the highest exponent. The degree is 2. The coefficient is -2. The degree is 2, so it's even, and my coefficient is negative. So again, I look at my chart. Degree -1, my degree is 2, so this is equal to 1 turn. So I have 1 turn, but most importantly, what are my end behaviors? Even and negative coefficient, that means I have down, down. So start and end like this with 1 big turn in between. So my graph looks more like this, and we can confirm it on decimals. We have negative 2x squared. And we clearly see the down, down scenario and the 1 big turn. I don't know if you've noticed the trend, but with those last practice problems, we've started with the leading term, okay? And the main thing that we extracted from the leading term is the degree and the coefficient, which told us the end behaviors, and we were able to conclude the number of turns. How? By taking the degree and subtracting it by 1. Okay, so we got a rough idea as to what the graph looked like. Now we're gonna look at a graph, look at the end behaviors, and then look at the number of turns, and this should tell us automatically the degree of the function and whether the coefficient is positive or negative. So now what we're essentially doing is we're going in this direction from here to here, okay? And the main thing I want to conclude from the graph is, what is the coefficient? Is it positive or negative of my leading term without knowing what the leading term is? So without knowing what the actual function is, or the polynomial is, or the leading term, can we conclude what the coefficient is and what the degree is? So looking at the end behaviors of this graph, what are they? I see up and up. So I'm going to go ahead and write that. That's the most important part, that I have an up scenario. Now I'm going to see how many turns I have. Just like we went from degree -1 equals the number of turns, we could also do number of turns plus 1 to get the degree, just to confirm whether it is an even or odd number. So I have 1 turn, 2 turns, 3 turns. So I have 3 total turns. So since I have 3 turns, what is the degree of the function? Well, plus 1 minus 1 in this direction. So if I have the degree first, then I subtract 1 to see the number of turns. If I have the number of turns first, then I add 1 to see the degree. So my degree is 4. So I have an even degree. My leading term degree is 4, which is even. And my leading term coefficient has to be, well, let's see. If I have up, what does my coefficient have to be? Well, I have this scenario up, so my leading coefficient has to be positive. And it's also, again, confirming, even though we already confirmed by actually solving for the degree, that it is even. Why? Because our degree is 4, but also because my graph's end behaviors are up. So it is positive as well. So just by looking at the graph, I was able to confirm the degree is 4, which is even, and that the coefficient is positive. Why? Because my graph has these end behaviors and this amount of turns. Answering the questions of the graph has 3 points on the x-axis. These are the graph's x-intercepts. These are also the graph's real zeros. So notice in class I've been using intercepts, x-intercepts, and zeros interchangeably because they essentially mean the same thing for the most part. Okay, so if we see the x-intercepts, we have an x-intercept at -5, 0, at 1, 0, and at 4, 0. My zeros are x equals -5, x equals 1, and x equals 4. So when it says what are the zeros, so let's say x equals -5, x equals 1, and x equals 4. If r is a real zero, then x minus r would be the factor. So -5, x plus 5. I have a real 0, 1, x minus 1 would be the factor. And I have a real 0, 4, so x minus 4 would be my factor. Now, before I answer multiplicity, I have it answered here because this is the answer key. But since I don't know what the multiplicity is, there's 2 things that I could see on the graph that will help me solve for the multiplicity, which is the total degree and whether it bounces or crosses at the point. So at -5, is my graph bouncing off this point or is it going through? So here we can clearly see at x equals 1, the line, which is the graph, goes through the point. So at x equals 1, I have a cross. Same thing with x equals 4. My graph goes through the point, so it crosses the point. So I have another cross at x equals 4. However, you guys see the difference between 1 and 4 and -5. At x equals -5, it does not go through the point. It doesn't go from this half to this half. It bounces off. All right, so this is called a bounce or a touch. And at x equals -5, I have a touch. So that means that my multiplicity must be even for it to bounce. My multiplicity must be odd for it to cross. Now, what is my total degree? How did I know my total degree was 4? Well, we determined that we have how many turns? 1 turn, 2 turns, 3 turns. If degree minus 1 is equal to the number of turns, if I know the turns first and I want to solve for degree, then I just add 1. So turns, right, number of turns plus 1 gives me the degree. Degree minus 1 gives me the number of turns. But since we're going this way, because we have the graph first, we look at the end behaviors. That's how we know the degree is 4. Because I have 3 turns, 3 plus 1 is 4. So my degree adds up to 4. How could these possibly add up? Well, I know this one has to be even. So now for the other examples, it's been 1, 1, 1. But does 1, 1, 1 add up to total degree 4? No. And plus, is 1 an even multiplicity. It has to be even because I have a bounce at that point. So the only possible way that these add up together with the consistency of what is happening in the graph, that it's crossing through this point, therefore the multiplicity must be odd, then the multiplicities have to add up this way. So we have 2, the multiplicity of x plus 5 is 2, the multiplicity of x minus 1 is 1, and the multiplicity of x minus 4 is 1 as well. So it says write the zeros of f of x as factors. These are the factors, which we just did. And then on top of that, we want to include their multiplicity. So now this one is to the second power. The multiplicity is equal to 2. This is to the first power, so multiplicity is 1 and 1. Finally, write the factors in polynomial, or write the polynomial in factored form with, look, this is telling you to write it with a coefficient a. This is important. I think it mentions this in the instructions as well. Find polynomial function of a graph with a coefficient a. So we have the polynomial function, but it wants us to include a coefficient a this time. Now that we have the coefficient a, it wants us to use the point 0, 200 to find a. So we want to solve for a. So we're going to use this function and use this point to solve for a. So if I have a point, what is a point? The point is just x comma y. So they want us to use 0, 200. Whenever I have a point given to me by a graph, this is just x comma y. Or in this case, we could also say x comma f of x, right? F of x is the same thing as y. So what it means is to use the equation that we have, which is, but instead of f of x, what am I plugging in for f of x? 200. You guys see how 200 is my f of x? So instead of f of x, I put 200. And instead of x everywhere, what x value is being given to me? 0. So I'm going to use the point 0, 200. This is my x. This is my y, or my f of x. So 0, I plug in for x. So everywhere I see 0, everywhere I see x, I'm going to put 0. All right, so do you guys see how I used the point 0, 200? All I did was use the value. So for x, I plugged in 0. And for y, or f of x in this case, I plugged in 200. And my goal is to solve for a. So I got to go by the order of operations. I have 0 plus 5, that is just 5. 0 minus 1, that is just negative 1. And then I have 0 minus 4, which is just negative 4. Okay, so that's PEMDAS. P is parentheses. E is exponent. So now I want to do 5 squared. Do you guys see that? 5 squared first before I even start multiplying across and all that. So 5 squared is just 5 times 5, which is 25. Then, now that I addressed the exponent, so I did parentheses, exponent, PEMDAS, multiplication and division. I see a bunch of multiplication. All these numbers right here, a times 25 times negative 1 times negative 4, they're all next to each other, so they're being multiplied. So this is 25 times negative 1 times negative 4. If I do this on my calculator, I get 100. Finally, I have a times 100. I'm solving for a, so since I have a times 100, to get rid of this 100, I have to divide both sides by 100. Cancel it out. So now 200 divided by 100 is equal to 2, and I solved for a. Okay, so now that I've solved for a using the point that was provided for me, so I solved for a. Look, this is me doing all the work. Do you see how I set up 200 is my f of x, and 0 is all my x values. I solved for a. A is equal to 2. This is my and then I rewrite the polynomial from this equation. You can see how this is still in factored form. The only difference between this and this right here is that now I included the a that I solved for. I'm going to say that again. The only difference between D, where I wrote it in factored form, is instead of a coefficient just a, since we solved for a, which is a is equal to 2, I included a as 2. Okay, because I solved for a, the coefficient, so I'm going to go ahead and write the coefficient into my final answer. All right, we're going to do a little bit of synthetic division. We're going to do problems 9 and 10. We need to understand how to do problems 9 and 10 in order to complete problem 11. Okay, so problem 11, the two things that we need to understand is synthetic division, how it relates to factoring, and also this idea where we have x squared plus a number. We did talk about it earlier in when we did problem number 8 with the complex conjugates. So we do really need to fully understand that and also understand how this applies to factoring, synthetic division. So before I even do that, I'm just going to do a basic problem where I have 235 divided by 15. This also could be written like this. This is probably how we're most familiar with seeing division. And we're trying to solve for 235 divided by 15, right? This setup is the same thing as this. The line, the horizontal line, means division, okay? A fraction is essentially just division, okay? So this is 235 divided by 15. So in order to complete this, this is called the divisor, what is actually dividing up the dividend. So if you hear me saying these terms, so the dividend is being divided by the divisor, and the solution of this is what's called the quotient. I'm going to write Q for quotient. And if there's a remainder, I'm going to write R. I always write the remainder over the divisor. All right, so we'll keep this in mind as we solve for 235 divided by 15. So 235 goes inside the box, 15 goes, the divisor goes outside the box. And then I look at 15 and I look at the first number right here, 2. Does 15 go into 2 at all? Is it possible for 15 to fit into 2? If so, how many times? 15 does not fit into 2. It's way bigger than 2. So it fits no times into the value 2. Okay, so now I look at instead of just looking at 2, I look at the first two terms and I see 23. Does 15 fit into 23? Yes, it does. It fits one time. So 23 minus 15, the one time it fit inside. We have 23 minus 15, which is 8. And then I bring down my 5, the last term. So now I look at this new value and I say, how many times does 15 fit into 85? 15 fits into 85 7 times, right? So that would be 15 times 7, which is 75. What is the remainder? 5 minus 5 is 0. 8 minus 7 is 10. Can I bring down any more values? No, since I can't bring down any more values, 10 is what is called my remainder. So the solution to this of 235 divided by 15 is 17, my quotient, plus the remainder, 10, over the divisor. Make sense? So is this a perfect factor? No. Whenever I have a remainder that is not 0, in this case I have a remainder of 10, I do not have a perfect factor. What if I had 15 divided by 3? 15 fits into 1 0 times. So now I look at 1 and 5. 3 goes into 15 5 times. So minus 15 is 0. I have no other values to bring down. I have a remainder of 0. So if I have a remainder 0, 5 is my solution, and it's a quotient. So when I divide by a factor or a divisor, and I get a number without a remainder, then what I have is a what I've found is a factor. So instead of seeing 15, I can write 15 is equal to 3 times 5. So keep this in mind. The reason that we do synthetic division is to see if we can find a factor. Okay? The factor helps me completely factor out the dividend. So that big number that we want to basically separate into little factors. Okay? That's why we use synthetic division. Whenever the remainder is 0, what we have are factors. When the remainder is not 0, then we have to include the remainder over the divisor. All right, so I'll come back to this idea, especially this right here. And then let's relate it to the problem number 9, where I have 3x squared plus 2x minus 1 divided by x minus 2. All right, except we're using synthetic division. In order to use synthetic division, you have to make sure that the dividend is in the form x minus c, okay, where x is to the first power, and then it's minus c, and c is the number that's being subtracted by x. All right, so in this case, do I have x to the first power? Yes. And is it minus c? Yeah, minus 2. So what does c equal in this case? Well, let me just line it up. X minus c. So c is clearly equal to 2. Once I've identified my c, I put it right here outside the box. This is what's being basically divided. The divisor, basically. But this entire thing is actually x minus 2 is the full divisor. Okay, now what goes inside the box? Inside the box goes the coefficients 3, 2, and negative 1. Do you guys see how I just chose the number in front of each term variable? So I have 3, 2, and negative 1. After I've labeled each coefficient and established what c equals, which is my divisor, I'm done with my box. Now I draw a line underneath, and the first thing I do is I put down the first value underneath the line. So now I have 2. Anything underneath the line gets multiplied by my c term, and the solution gets added to the next column over the line. So I'm always going below the line, above the line, below the line, above the line. When it is above the line, I add. When it's below the line, I multiply. Okay? So that's why the first thing we bring down is that 3. All right, so below the line, I multiply to my c term. So I have 2 times 3, which is 6. My solution gets added to the next column underneath, and I just add straight down. So 2 plus 6, above the line I add. 2 plus 6 is 8. Oh, I'm below the line again. Below the line I multiply. 8 times 2 is 16. I'm above the line again, so I add. And negative 1 plus 16 is 15. And then I'm done. Okay, so there's no other values to bring up, so there's nothing to add or multiply. This last term right here underneath the line this is basically my answer, my quotient, but I have to basically relabel this. So that first term is always going to be my remainder. This next term is going to be my c constant term, And this next term is going to be my x. And if I had more values, which I don't, I'm done at 3. But if I had more, it'd be x squared. If I had more, it'd be x cubed. And I would keep going down the line. Okay, but in this case, I stop at 3x. All right, so what these are coefficients. So I have 3x. And this is a constant term, so plus 8. It doesn't have a variable x. So my quotient so far is 3x plus 8 with a remainder of 15. How do we write the remainders? Remainder over the divisor. What was my initial divisor? X minus 2. This is my final answer. Okay, let's try another problem. Okay, so for this next problem, problem number 11, same process, where I have 2x squared plus x minus 15 divided by x plus 3. This is my dividend, and below is my divisor. Okay. And we're trying to solve for the quotient, what it equals, okay? Remember, we have to, whenever we use synthetic division, we have to make sure that the divisor is in the form x minus c, okay? Where x is to the first power minus c. Right now, I don't see x minus c, I see x plus c. So if that is the case, then I have to rewrite this as x minus a number. Okay, what would my c term possibly have to be so that I still have, or so that it's still true that that I still have x plus 3? Well, if I have x minus a negative 3, isn't that the same thing as x plus 3? The only reason I've done this is that so that we successfully or accurately identify what c equals. C does not equal 3 because it's not in the form x minus c. C actually happens to equal negative 3. Okay, that's why it's really important that x is to the first power and that we have it written with a minus sign, not a plus, so that we know specifically what our c term is. So c is equal to negative 3. Make sense? Okay, what goes inside the box? The coefficients of my dividend. So I have 2. There's no number there, but what's the number in front of x? 1 and negative 15. 2, 1, negative 15. Okay, so I'm done labeling. Now I draw my line, bring down the first value underneath the line. When it's underneath the line, I multiply by my c, and my solution goes up top. So below, up top, below, up top. So below the line, 2 times negative 3, which is negative 6. Above the line, add. 1 plus negative 6 is negative 5. Below the line, multiply. Negative 5 times negative 3 is a positive 15 above the line. And then I add. And I get negative 15 plus 15 is 0. So this is basically my quotient. I just have to represent these values correctly. So what is this first one again? My remainder. So in this case, I have a remainder 0. This is important as I relate it back to factoring. All right, so keep this in mind. This is my c constant term, and this is my x coefficient. So I have 2x minus 5 with a remainder 0, so I'm not even going to write it. What this is saying is that when I divide this polynomial by this polynomial, I get the solution 2x minus 5 with no remainder. So this is similar to when we did 15 divided by 3, and I got 5. 5 doesn't have a remainder. So what does that mean? That means that 5 and 3 are both factors of 15. Again, when I divide two values and I get a number with no remainder, or a value with no remainder, that means that the value I've just found is a perfect factor, or just a factor of the initial dividend. Unlike this one, when I did 235 divided by 15, I happen to get 17 plus 10 over 15. Is 15 a factor of 235? No. Is 17 of 10 divided by 5 also a factor of 235? The answer is no. How do I know this? Because I have a remainder that is not 0. Here, when I have a remainder equals 0, I've found a perfect factor. So, keeping this in mind, so if this is true, I have no remainder. I could rewrite this if I wanted to as 2x minus 5. Just like 15 divided by 3 is equal to 5. So then 5 times 3, 2x minus 5 times x plus 3 are factors, when I multiply together, equal to 2x squared plus x minus 15. How do I know I'm done factoring? When each x value is raised to the first power. Notice here, I'm not done factoring what I started with because I have a squared. That's why this divides into two nice factors, each raised to the first power. So this is the fully factored form. This would be considered expanded. Okay, so do you guys see how synthetic division helps me factor or find perfect factors with no remainder? As long as I get no remainder, I have found a perfect factor. All right, so going back to this idea as well. Oh, right here. The shortcut to square root. So I want you guys to really rely on this. We did examples with perfect squares, but let's say I have x squared minus 6, for example. Okay, so I have x squared minus a number, so my solution is equal to x equals plus or minus the square root of what? The square root of the letter, right? So in this case, the square root of 6. So what are my zeros? Well, my zeros are x equals positive square root 6 and x equals negative square root 6. How would I write these as factors? This would be x minus square root 6, and this would be x minus a negative square root 6, which would be x plus square root 6. Okay, so keep that in mind, that this formula works for all numbers. That's why I just wrote a. Even if they are not perfect squares, we just happen to have like little funky square roots. Okay, so the same idea applies. So now let's look at problem number 11. Let's look at the answer key. Find all real and complex zero of the function using a graphing calculator to graph the function and identify one real zero. So I'm going to read that again. Use a graphing calculator to graph the function and identify one real zero. If we're able to identify a real zero, then what we have is a factor. Okay, so let's graph this on our calculator. It's telling me to take the polynomial function, use a graphing calculator to graph the function. So graph this, f of x is equal to this entire function, to identify one real zero. So let's go on Desmos and let's graph f of x is equal to, okay, so can we identify a zero? So this is similar to problem number 7. How do we identify a zero? By looking at the graph and seeing where I have an x-intercept. So where do I have an x-intercept? At 3, 0. So this is a 0. What is my 0? At x equals 3. So if I look at the answer key, you can see that I found a 0, and that 0 is x equals 3. And I also included what's happening at that 0. What is happening? That I have a bound situation. All right, that might help eventually, but I'll show why that makes sense in a second. But the important thing is that you're able to identify a 0 and let me know the factor of that 0. So just like the chart we've been doing, we identify the 0 and then we write the factor of that 0. So if my real 0 is r, just like over here, if my real 0 is -4, what is the factor? X plus 4. If my real 0 is 3, then look at what I'm dividing my function by. What am I dividing my function by? X minus 3. Do you see that? All right, so let's actually do this problem separately. All right, so how did I know that I was going to divide this by a factor? Well, I graphed this on my calculator and I saw that I have an x-intercept. I saw that I have an x-intercept at x equals 3. So what did I just identify? I identified a 0. Any 0 is going to be a factor of the polynomial. So at x equals 3, I have a 0, a real 0, and that 0 is a factor of x minus 3. So what that means is that I can go ahead and divide this by x minus 3, and watch, you're going to see that I'm going to be able to reduce this using synthetic division. So ultimately, I want to take this big polynomial and be able to factor it out like this, okay, into nice factors, parentheses. Each factor hopefully has x to the first power. That is how I know I'm done factoring, okay? So that's what I want to do. Right away, I know that one of these factors is x minus 3. How do I know that? Because on the graph, at x equals 3, I have an x-intercept. So automatically, that means I have a factor at x minus 3. So now, I'm going to use synthetic division to find out what this is equal to. Right? So that this is another classic scenario where I have 15 divided by 3 is equal to 5. So I want to be able to write this as blank times blank equals 15. So right away, I know 3 is a factor of 15. Let's say I didn't know 5 was a factor of 15. So that's exactly how this problem is set up. That 15, I know 3 is a perfect factor of 15, but I just don't know the solution. I'm going to solve for it. I'm going to do the math and I'm going to solve for it. But I do know that 3 is a factor. I just have to figure out what this other factor is so that I was able to, I know for sure that 3 is a factor. I want to find out this other factor so that I know that 3 times this factor is equal to 15. So that's exactly what I'm doing here. I know this is a factor, but I'm trying to figure out what this factor is over here. So how do I do that using synthetic division? First of all, I have to make sure that my divisor is in the form x minus 3, and c in this case is equal to 3. So 3 goes on the outside. Then the coefficients, what's the coefficient of x to the 4th power? 1. X cubed, -6. 14x squared, 14. -30x, -30. And 45. All right, so now that I'm done labeling, I put my line, I bring down the first value underneath the line, multiply it to my c. 1 times 3 is 3. Then I add. -6 plus 3 is -3. Below the line, multiply. -3 times 3 is -9. And I add. 14 minus 9 is 5. Below the line, multiply. 5 times 3 is 15. -30 plus 15 is -15. 15 times 3 is negative 45. Oh, look at that. My remainder is 0, as it should be. Why? Because I found a perfect factor, which is x minus 3. So that means this also has to be a perfect factor. So negative 15 is my c. 5 is my x. 3 is my x squared. And 1 is my x cubed. And if I had another one, it'd be x to the 4th, and I keep on adding. Okay, and this one right here is my remainder. So these are all going to be coefficients of these values. So I have 1x cubed minus 3x squared plus 5x minus 15. And what I've done is I've found the other factor. What I did was 15 divided by 3, and I just, right now, all I did was solve for 5. I've solved for the other factor. X to the 4th minus 6x cubed plus 14x squared minus 30x plus 45 divided by x minus 3 is equal to x cubed minus 3x squared plus 5x minus 15. So just like 15 divided by 3 is 5, then 5 times 3 is equal to 15. So I'm going to go ahead and rewrite this as x minus 3 times x cubed minus this. This is equal to this long polynomial x to the 4th minus 6x cubed and so forth. Okay, so all I've done was slightly factor this. All right, so now how can I continue to factor this polynomial? Here, I give you a hint. I say, oh, look, there's some grouping going on. How do I know I have grouping? Well, if I focus here, am I done factoring this factor right here? Yes or no? What I've highlighted. Yes, why? Because x is to the first power. Is x to the first power here? No, I have x cubed, which tells me that this section right here, I must continue to factor. All right, so that I have a bunch of factors that are raised to the first power like I do here. All right, how do I know I'm using grouping? Because I have 1 term, 2 terms, 3 terms, 4 terms. Whenever you have 4 terms, you want to try to use grouping. So I'm going to isolate this, really hyperfixate on this. And whenever I have 1, 2, 3, 4 terms, I want to group the first two. So x cubed minus 3x squared here. And then group the last 2 terms. And don't forget, we still have the factor x minus 3. We're just going to remember it at the end when we write down all the factors. We want to see if we could factor this slightly, okay? So what do x cubed and negative 3x squared both share? They both share an x squared. So when I take out an x squared from x cubed, I'm left with x. When I take out an x squared from negative 3x squared, I'm left with negative 3. What do these both share? They both share a 5. When I take out a 5 from 5x, I'm left with just x. When I take out a 5 from negative 15, I'm left with negative 3. And I can always double check. What's 5 times x? 5x. What's 5 times negative 3? Negative 15. Same thing over here. What's x squared times x? X cubed. What's x squared times negative 3? Negative 3x squared. So that's how I verify, okay? But the whole point of factoring by grouping is so that when you get to this step, you should see that both factors match and they both equal x minus 3. So you only have to write that once, the factor that they both share. And then the other factor is basically what is left over, x squared and 5. So I have x squared plus 5. All right, so again, what I've done is factor out. This is a factor of this right here. And what did I use? I used grouping to factor this out as much as possible. And don't forget, I still have this x minus 3, so I have to bring that down right here. Make sense? So now I have this one's coming from this, and then these two are coming from this right here. And this is a simplified version or a factored version of this. Make sense? Okay. X is to the first power here. X is to the first power here. X is to the second power. Oh, man. But I only have two terms. Ooh, don't I have something in the form x squared plus 5? X squared plus a. So what do we do when we have something in the form x squared plus a? When I have x squared plus a, I basically just have x is equal to plus and minus the square root of a. So I'm going to factor this one out. So this one should factor into something like this. Why? Because I have an x squared. I need to make sure that each x value is raised to the first power. So I have x squared plus 5 or x squared plus a. So that means that I have x is equal to the plus and minus of square root 5 times I, because it's plus. So that means I have a complex number. So this means x is equal to square root 5 I, and x is equal to negative square root 5 I. So just like we identify the zeros, these are my zeros. Like when we do the chart, what would the factor be? All right, the factor for this one is x minus square root 5i. And the factor of this one would be x plus square root 5i. All right, so that's important because I want to factor this out. I don't want to just have x equals as x equals. I want to fully factor this. So I have x minus 3 times x minus 3. So notice all my factors are raised. All my x's in each factor are raised to the first power. And what I've done is I've identified all my zeros. Look at this, x minus 3 repeats. So I can write this if I wanted to as x minus 3 squared. Then I have x plus the square root 5i and x minus the square root of 5i. Notice this one is the repeated zero that we started with. Remember when we looked up the graph? And at 3, what happened? I had a bounce. That's why I wrote bounce, because look, what's the multiplicity of x minus 3? The multiplicity is 2, and that makes sense because on my graph I have a bounce. So that's why one of the factors also again ended up being x minus 3, not just the 0 we identified, but also as we continue to factor. Why are these not on my graph? Why do I not see these zeros on the x-intercepts? Well, again, because they are imaginary. So whenever we have I, these are still zeros, but they're not real zeros. So that's why we don't see them on the graph. So if I go back to my answer key, right now we're doing problem number 11. It just asks you to list the zeros. We have a 0 at x equals 3. We have a 0 at x equals I square root 5 or square root 5i. And we have an x at negative square root 5i. Again, complex numbers always come in pairs, positive and negative. And this gives you basically the same thing, the same rundown that I wrote out. the key thing here is to remember that, okay, we have x squared plus 5. Also, the main idea is that x minus 3, how did we get x minus 3? How did we know to divide by x minus 3? Because we identified a 0 at x equals 3. And that's it. That's all it's going to ask you for, is to identify the zeros with that information. So we have to use synthetic division to narrow it down, and then hopefully we can use other forms of factoring. Like in this case, I used synthetic one time. Then I saw I have 4 terms here, so I use grouping. And then after I used grouping, I ended up with this scenario. And then here I see x squared plus a number. So whenever I have x squared plus a number, then I could use this little formula, x is equal to plus and minus I square root a. However, if I do decide to do that, I have to remember that these are also factors, okay? So ultimately, these are all of my factors. And I mean all of my zeros. So now for problems 12 and 13, we're dealing with polynomial functions that are fractions. This is known as rational expressions. So again, rational expressions are just a polynomial over another polynomial. Okay, so notice we have a polynomial over another polynomial. X squared plus 9 is a polynomial. X plus 4 times x plus 1 is another polynomial. To solve for the domain, the first thing we're going to do is we're going to set the denominator equal to 0. Why am I doing this? If you guys remember back in chapter 1, the domain is what x values am I allowed to plug in? Can I plug in any x value I want? Well, for the most part, domain is all real numbers. But whenever I see a fraction, that's a red flag, or a square root, that's another red flag, those two indications, when a polynomial is equal to a fraction or a polynomial function is equal to a square root, that means that I can't always plug in whatever x values I want. Some x values give me problems. For example, with fractions, I don't want my denominator to equal 0. So I have to be careful what x values I plug in here or here. That could potentially make my denominator equal to 0, because if I plug in x and my y is a fraction of a number over 0, then I have a problem. That's an undefined point that I do not want to include in my domain. So right away, when I see a polynomial function is equal to a fraction, I'm going to set the denominator equal to 0. So what is the denominator? This top part is my numerator. This bottom half is my denominator. I'm going to set my denominator, like it's telling me that's exactly what I'm supposed to do. Set it equal to 0 and solve for x. So I have a fraction and a fraction equal to 0. Whenever I have something like this in factored form equal to 0, I set each factor equal to 0 as well. So I have this, and I have, I'm just going to copy all this, x minus 1 equal to 0. That's the next step, because my goal now, after I set the denominator equal to 0, my goal, my objective is to solve for x. How do I solve for x when it's factored? Set each factor equal to 0. Now, I have x plus 4 is equal to 0, so to solve for x, I'm going to add 4. So now I have x is equal to, subtract 4. So I'm going to, to get rid of a positive 4, I got to subtract. Minus 4 to both sides. So now I have x is equal to negative 4. Over here, I have x is equal to 1. So x cannot equal negative 4. You could have also changed these signs. Set the denominator cannot equal 0 like we've done before. As a reminder that we're solving for the x values that I cannot include in my domain. All right, so when I'm excluding negative 4 from my domain, and I'm also excluding 1 from my domain. Why? Why am I excluding these? Why are these x values not included in my domain? Why am I being restricted from plugging these x values in? Because they make my denominator equal 0. For example, if I do -4 and I plug in -4 for x, what happens to my equation? So I'm plugging in -4 wherever I see x. All right, now it's time to simplify. -4 minus 1 is -5. -4 plus 4 is 0. This is going to give me... Ooh, what did I do? This is going to be 16 plus 9. Okay, whatever. The point is that the denominator, 0 times -5 is 0. So look, I'm going to get a number over 0. Is that a defined number? No, it's undefined. So what happens when I plug in the x value that I just solved for? They make my denominator 0. That's exactly why we are excluding them from our domain. Because again, what is domain? What x values am I allowed to plug in? You are not allowed to plug in. You're allowed to plug in everything else except -4 and 1. Why? Because if I plug in -4 or 1, I get something. My result is something over 0, which is undefined. So I have to exclude these from my domain. All right, so that's exactly how I would write my domain. All right, same thing. We're going to do the same process for problem number 13. Again, domain. I see a fraction, so my domain is not all real numbers. There's going to be a restriction. With fractions, I have to set the denominator equal to 0. So this is the denominator. I'm going to set it. Ooh, I didn't want to set all of that. I'm going to set the denominator cannot equal 0. And I'm going to solve for x. So x is equal to -3. Notice if I plug in -3 here in my denominator, I'm going to get some number up top. Doesn't really matter. But if my denominator is equal to 0, that is a problem. Why? Because f of -3 is equal to -3 plus 3 is 0. Then -3 squared is 9. Minus 3 is 6. Minus 12 is -6. That's why we're excluding it from the domain. So x cannot equal -3 for this one. All right, pretty simple. All right, so now the next thing it's asking for is the vertical asymptote. What is that? So this is a new idea. Notice we have polynomial functions that are fractions. These are called rational expressions, and these graphs look a little bit different. So they're a little bit untraditional. So we're used to graphs that look like this, or look like this, or look like this. Something of this form, even when they're transformed a little bit. Okay, so we're used to these traditional graphs. Whenever we have a polynomial function equal to a fraction, so like right now we have x squared divided by, okay, cool. And then I have x plus 4, I think it was, and x minus 1. Okay, do you guys see how these graphs look a little bit different? All right, do you guys see the vertical asymptote right here? There's another vertical asymptote right here. These are dotted lines, invisible lines that our graph gets close to but doesn't cross. Even this horizontal asymptote, it gets close to it. Look how close it gets, but it doesn't quite cross. Horizontal asymptotes, sometimes your graph does cross them. So if you guys look closely right here, we do have a graph crossed right here. But vertical asymptotes, the graph never, ever crosses them. Now, in relation to problem number 2 is because it's closely related to the domain. So we just did the domain, and you're going to see how it relates to the vertical asymptote. So I graphed the problem. You guys can see that we have vertical lines where? We have a vertical line at -4. Do you guys see that? And a vertical line at 1. Wait, isn't that what our domain restricted? Yep, -4 and 1. I have a vertical asymptote whenever my solution, like you guys see how the reason that we're taking away x equals -4 from our domain is because when I do plug it in, I get something over 0. Whenever I get a number over 0, that means I have a vertical asymptote. So vertical asymptotes and holes, this is a new idea. If I show you guys right here, the difference, vertical asymptote is the line, the vertical line that our graph, the green graph approaches but doesn't cross. The hole is that open circle. All right, so how do I know I have a hole and how do I know I have a vertical asymptote? They both happen when our denominator is 0. The only key difference is that I have a hole when I plug in that value, I get 0 over 0. So it's the same process. Vertical asymptotes happen when the denominator equals 0. So you can set the denominator equal to 0 again, solve for x. The x values, you're going to plug them back into the function. So f of -4, you plug in -4 right here, right here, right here, and then you fulfill the equation. So you do all the math. Notice when you plug in f of -4, it equals 25 over 0. So if I have a number over 0, and that number up top is a non-zero, so it's a number other than 0, that means I have a vertical asymptote at x equals -4. When I plug in 1, because the other thing that made my denominator 0 was 1, when I plug in 1 for x, so I have 1 squared plus 9, 1 plus 4, and 1 minus 1, I get, my result is 10 over 0. Again, do I have a non-zero up top? Yes, so that means if I have a number over 0 and it's not 0 over 0, that means I also have a vertical asymptote at x equals 1. So when I graph this problem, look, I'm graphing this problem. We clearly see the vertical asymptote at x equals -4. How do I get a vertical line? How do I get a horizontal line? This might be a refresher. Y equals 2. Do you guys see how that gives me a horizontal line at y equals 2? Or y equals 4? Or y equals 10? These are all horizontal lines. If I want a vertical line, x equals 2 or 3. X equals 6. These are vertical lines at x equals a number. So that's why vertical asymptotes, the equation to make a vertical line is x equals a number. So x equals -4 is going to be that invisible line that my graph approaches but does not cross. So again, if we see here, we have a vertical line x equals -4, that dotted line that my graph is getting really, really close to, but it's never going to cross. It approaches this vertical line, but it does not cross it. All right, so domain and vertical asymptotes are closely related because they both happen when the denominator equals 0. The only next step is to plug them back into the function to verify, to make sure that when you plug these x values back in, you get a number over 0, and the number up top has to equal a non-zero for you to have a vertical asymptote. When you get 0 over 0, like this example, look at x equals 2. When I plug in 2, look at my result. I plugged in 2 for x, I plugged in 2 here, I plugged in 2 here, I plugged in 2 here. This is my original function, and I found that this was restricted from my domain, so I plugged in 2 to see what it gives me, and the solution was 0 over 0. If you have 0 over 0 at x equals 2, 1, 2, then you don't have a vertical asymptote, you have a hole. So that's the difference. Vertical asymptotes look like a number other than 0 in the numerator. So like 2 over 0, 3 over 0. That tells me I have a vertical asymptote. I have a hole if my solution is 0 over 0. So that is the key difference. All right, now let's see. That was problem number 12. Let's do the vertical asymptote for problem number 13. Let's see if we have one. Again, I have a vertical asymptote when I have a non-zero over 0. Either way, I have to set the denominator equal to 0. So just like we did with domain, when we set the denominator equal to 0, we got x equals or cannot equal -3. So same thing applies here. But now the additional step is plug it into the function to see what your result is. So plug x equals -3 back into this equation So I'm going to do negative 3 squared plus negative 3 and negative 3 plus 3. What do I get? I obviously get 0 in the denominator, but what's important here is that I make sure I look at what I get in my numerator. Again, I have a non-zero over 0, so I have a vertical asymptote at x equals negative 3. So I have a vertical invisible line at x equals negative 3. Now let me verify it just so you guys can see how it looks like on the graph. Now, all right, I'm going to go ahead and graph it. And then remember, we have a vertical asymptote at x equals negative 3. And that's that dotted invisible line right here. That, again, my red graph is getting really close to it, but it's not going to cross this vertical asymptote. So for this scenario, we only have one vertical asymptote. For the last scenario, we had two vertical asymptotes. It really depends on how many values make the denominator 0 when we solve for x, and whether those x values, when I plug them back into the equation, they give me a number other than 0 over 0. All right, so now we want to verify whether the graph has a horizontal asymptote, yes or no. How do I know I have a horizontal asymptote? So this is the next idea. Rational expressions, polynomials that are equal to a fraction, like these examples right here, where we have a polynomial equal to a fraction, we're able to look at the numerator and identify the leading term of the numerator, and we also want to identify the leading term of the denominator. Why do we want to do that? We did a lot of practice with that. The reason we want to do that is so that we could determine what the degree of the numerator is and what the degree of the denominator is based on the leading term. So if I look over here and I see x squared, just focus on the numerator. I want you to tell me what the leading term is. Notice I have one term, two terms, three terms on my numerator. What is the leading term of my numerator? What is the term with the biggest exponent? This has exponent 2. This has exponent, we don't write it, but it's basically exponent 1. And this one is x to the 0 power. Again, what does x to the 0 power equal? 1. So we never write it. So this technically has an exponent of 0. So between 2, 1, and 0, this one has the highest exponent. So this is my leading term. So I'm going to go ahead and write my leading term is x squared. Okay, what's my leading term of my denominator? Well, now I only have two terms, x, and x plus 3. I mean, x and 3, these are my only terms. So between these two terms, obviously x is the one with the leading term exponent. This is x to the first power. And technically, 3 has an exponent of x to the 0 power. Again, x to 0 is just 1, so we never write x to the 0 power. So between 1 and 0, 1 is the highest exponent. So my leading term is x. Okay, so now that I look at my leading term, I want to say, what is the degree of this function? The degree is just the exponent of the highest term, of the leading term. So the degree is equal to 2 here, and the degree is equal to 1 here. This is known as n. The degree of your numerator is known as n. The degree of your denominator is known as m. So right now I'm going to rewrite this a little bit neater. But here I have n equals 2. The degree of my numerator is 2. And the degree of my denominator is 1. So right now I'm looking at these numbers and I'm asking myself, okay, in terms of n and m, is n bigger than m? Is m less than m? Or is n equal to m? So I see 2 is bigger than 1, so n is bigger than m. So if that's the case, when n is bigger than m, then there is no horizontal asymptote. Instead, we have an oblique asymptote. We'll come back to this If we have an oblique asymptote, again, this is where synthetic division comes in. So we're going to have to know how to solve this with synthetic division to solve for the oblique asymptote. So we'll come back to that. Before we finish that, I want to see if we can identify the horizontal asymptote for problem number 13. What the degree of our numerator is. Before we do that, what is the leading term? So between x squared and 9, what is the term with the highest exponent? X squared. So the degree of the numerator is 2, so n is equal to 2. Now, I have to think about the denominator a little bit. It's already in factored form, so it's kind of hard to tell what the degree of the denominator is. But if you guys remember, what is the multiplicity of x plus 4? 1, 1, right? These are both 1. Because they're 1, we don't write them down. But in the back of our minds, we know that this is raised to the first power. When we were doing the charts, like here, all the multiplicities must add up to the total degree. So we have two options here. We could either go by adding up the multiplicities. So 1 plus 1, the degree must be 2, m equals 2. Or, we have two options here. We can do that, or we could do the math to write this in expanded form. So if I were to FOIL this problem out, I would get x times x, which is x squared. X times negative 1 is negative x. 4 times x is 4x. And 4 times negative 1 is negative 4. So this simplifies to negative x plus 4x is plus 3x. So again, now I can honestly just replace this with this, and it's very clear that my leading term is x squared again, and the degree is equal to 2. So there's really two ways to go about this. Noticing that remembering that multiplicities add up to the total degree, or just going ahead and expanding it to clearly see what the leading term is. Either way, I got to the same answer, that the degree of the function, 1 plus 1, the multiplicities, adding those together, or looking at the leading term, the degree is 2. So in this scenario, I have n is equal to m. Now, what happens if n is equal to m? If n is equal to m, then the asymptote is equal to y is equal to a over b. So if that is the scenario, we have to look at the leading term coefficients. So the number in front of our leading term here and the number in front of our leading term here. What is the number in front of x squared? Well, that number is 1, right? Same thing here. When we expanded it, what is the number in front of x squared? 1 again. So my leading term, we now use the letters a and b. The coefficient of my leading term over here is 1, and the coefficient of my leading term here is 1 as well. So when n is equal to m, then y is equal to a over b. In this case, y is equal to 1 over 1. So my horizontal asymptote is at y equals 1. And let's confirm it. It's 9 over x plus 4 times x minus 1. I just want them to graph it, but we should have a horizontal asymptote look at y equals 1. So that explains the horizontal line right here at y equals 1. How do I get a horizontal line again? With y equals a number. How do I get a vertical line again? With x equals a number. So the vertical asymptotes, remember how we solved those? The horizontal asymptotes are just this right here. For problem number 13, remember we got no horizontal asymptote. Why? Because n was bigger than m. If I have a scenario where n is bigger than m, there's no horizontal asymptote. So what I have is an oblique asymptote. If I have an oblique asymptote, what are the steps to solving for the oblique? We have to use I wrote long division, but you could also use synthetic division. It's probably the easiest one to use. And then once you get to synthetic division, you ignore any remainder. Okay, so let's go ahead and use synthetic division for this problem. We have x squared plus x minus 12. Remember, whenever we're going to use synthetic division, the denominator has to be x to the first power minus a number c. So if it's written as x plus 3, I have to rewrite it as x minus a number. So in order for it to still be true, x plus 3 is the same thing as x minus negative 3. So my c term is actually equal to negative 3, not plus 3. So careful with that. When we have x plus 3, my c is equal to negative 3, not plus 3. The reason we identify c is because then we start to write c on the outside of our box. What goes inside my box are the coefficients of each term in my numerator. So this is one term, x squared. What is the coefficient, the number in front of x squared? That number is 1, so I write 1. What is the coefficient of x, the number in front of x? That number is 1 again. And what is the number, the last term, negative 12? That is also a coefficient because, again, technically, those integers by themselves have a variable x to the 0 power. We just never write it because, again, it equals 1. But that is a coefficient, and that is negative 12. All right, so now the first step of synthetic division is to bring down the first number, which is 1. I almost wrote 3 instead of negative 3, right? We did all that work to make sure that c is equal to negative 3, and I almost wrote it wrong. So my c is equal to negative 3. All right, so the first thing we do is bring down our first term coefficient underneath the line. Anything underneath the line we multiply out. So 1 times negative 3 is negative 3. Now my solution goes above the line, so I'm always going below, above, below, above. Above the line, I add down. So 1 plus negative 3 is negative 2. Below the line, multiply. Negative 2 times negative 3 is 6. Above the line, add. Negative 12 plus 6 is negative 6. This term, the first one, is always my remainder. This is my c constant. And this is my x coefficient. So this is 1x. I could just write x minus 2. And then with a remainder of 6. But notice with oblique asymptotes, ignore any remainder. So we're just going to ignore that minus 6. We're going to ignore it. It doesn't matter for the oblique asymptote. And just focus on the result. Y is equal to x minus 2. This is going to give me the diagonal line. So oblique asymptotes, they look like, so notice we've had vertical asymptotes and horizontal asymptotes. Now we have oblique asymptotes. So whenever we don't have a horizontal asymptote, we have an oblique asymptote, which is a diagonal line. So instead of having that horizontal line, we have a diagonal invisible line. So in order to write a diagonal line, we have y equals mx plus b. So that's what we solved for. That's why I said it equal to y. That's how we're going to get that diagonal line. So oblique asymptotes happen when we don't have horizontal asymptotes. They happen when n is bigger than m. In order to solve for the oblique asymptote, we have to use either synthetic or long division. So look, I use synthetic division here. This number is my remainder. We ignore the remainder and we focus on these variables right here. This is the coefficient of my x. This is my c, my constant, minus 2. So y is equal to x minus 2. This is the equation of my oblique asymptote. All right, so notice on the graph, share it. Look, we have a vertical asymptote at x equals negative 3, but also this oblique asymptote. Look, we have an oblique asymptote at y equals x minus 2. All right, the final things in the packet is defining the x and y intercepts for both problem 12 and 13. So we'll get some practice with that. To solve for the x-intercept, so again, these are problem 12 and 13. They're both fractions. They're polynomial rational expressions, which is a polynomial over a polynomial. It's still a graph. It's just a funky graph. It looks a little weird. But we can solve for those x-intercepts. So notice there's an x-intercept here, right here. And there's an x-intercept here. So these are points that cross where my graph is the red graph that cross the x-axis. So we can look at the graph and identify them, like this is 3, 0, and this is negative 4, 0. But to algebraically solve for them, how would I do that? So it's in my instructions. X-intercepts, just set the numerator equal to 0 and solve for x. Okay, that's all we have to do for x-intercepts. So notice we have f of x is equal to x squared plus x minus 12 over x plus 3. What is my numerator portion? This right here. So this is what I'm going to set equal to 0. It's telling me to set the numerator equal to 0 and solve for x. So notice this is a classic factoring problem. Whenever I see 1, 2, 3, or 3, I want to label A, B, and C. A right now is equal to 1. B is equal to 1 as well. And C is equal to negative 12. If A is equal to 1, then I suggest you factor into two parentheses and put x and x like this. Then how do I fill in the blank? How do I fill in this blank? How do I fill in this blank? Well, I find factors of my C term, negative 12. What times what gives me negative 12? That when I add them together, I get a positive 1. Well, I know 12 is 6 times 2, but those combinations do not help me add up to 1. So what about plus 4 and minus 3? One of these has to be negative in order to get a negative 12, right? Negative 3 times 4 is negative 12. And also negative 3 plus 4 gives me 1x, my B term. So now that I found my factors, because again, the objective was to set the numerator equal to 0, which I did, and then solve for x. So in order to solve for x, I could use the quadratic formula, right? Because I have 1, 2, 3, A, B, C. I could use the quadratic formula, or I could factor. So there's two options to solve for the x values. So after I factor, I set each factor equal to 0, and I solve for x. So now my x-intercepts are negative 4, 0, and 3, 0, because I got x equals negative 4 and x equals 3. Let's verify. This looks like negative 4, 0. This looks like 3, 0. So again, we can clearly see this on the graph, but to algebraically solve for them, so showing some math and doing some work, we set the numerator equal to 0 and solve for x. Usually, whenever we solve for x-intercepts, this has been the constant trend, the numerator has to, or just in general, we have to factor. Factor or use a quadratic formula or use the square root method to get the x values that are my x-intercepts, my zeros of my function. Now to solve for, or let's do the same thing. Or actually, we'll just solve for the y-intercept. This one's pretty simple. All we have to do is set x equal to 0 throughout the whole equation. So just like with the x-intercepts, we started with the original equation, right? And I showed you how we dissected the numerator equal to 0. For the y-intercepts, we start with the original equation. And very simple with y-intercepts, all we have to do is set x equal to 0. We're solving for any points that are on the y-axis. So x-intercepts, we're solving for these points. Y-intercepts, we're solving for the points on the y-axis. So look, I should get, after doing all my work, I should get negative 4, 0. And we start off with the original function, and it says set x equal to 0 because y-intercepts happen when x equals 0. So plug in 0 for everywhere that I see x. I have 0 squared, which is equal to 0, plus 0, which again is equal to 0. So in the numerator, I'm left with negative 12, and 0 plus 3 is also 0. So I have, when x is equal to 0, I have negative 4. So the y-intercept is 0, -4. So look, this graph just shows me plotting everything all together. So we have -4, 0, and 3, 0. Those were my initial x-intercepts. Then we have -4, 0. That was another y-intercept that we just solved for. Vertical asymptote at x equals -3. That's, again, what we initially solved for. That was the first thing we solved for. And this y equals x minus 2 is this oblique asymptote altogether. Okay, so that would be, like, again, the whole point of chapter 3 is basically seeing how we can dissect certain portions of our function, our polynomial function, to get a good idea of what our function, our graph, looks like on a graph without even graphing it. So look, we're able to identify those vertical asymptotes. We're able to identify whether it has a horizontal asymptote or oblique asymptote. We're also able to identify the intercepts x and y, so that we can ultimately do our best to graph it, do a rough graph of the polynomial function. So then now, let's do the same thing with this other problem. That was problem number 13. Let's do the same thing over here. All right, so to solve for the x-intercepts, again, what do we have to do? Set the numerator equal to 0. So this is my original function. This is my numerator. Set it equal to 0. So then now I have x squared is equal to -9. X is equal to, whenever I have x squared plus 9, remember, this is another classic scenario of x squared plus a. Whenever I have plus a, then when I use the square root method, I have plus and minus the square root of ai, imaginary number. So because my solutions for x are both imaginary numbers, they are not on my graph. So do I have any x-intercepts in this scenario? If my only two x-intercepts, or my x values, where I have x equals, and I get x equals 3i and x equals -3i, are these going to be x-intercepts? Can I possibly make these as points? Are these graphable points if they have I involved? No, because they're imaginary. So these are not, I do not have x-intercepts. Why? Because these are complex zeros. So no x-intercepts for this problem exist on my graph. Okay, so this one we have to think about just a little bit, but if we look and we are able to identify that we have x squared plus a number, that means that we have I, and whenever I have I, this is not a real zero. If it's not a real zero, it is not an x-intercept. And then finally, what is the y-intercept? The y-intercept is when we set x equal to 0. So again, starting off with that original function, what are we doing? Plugging in 0 for x. Everywhere that we see x, plugging in 0. And then simplifying. And for this problem, we have a y-intercept that is a fraction. That's completely fine. And this is what it looks like. So if I were to graph this entire function, x squared plus 9, and we see everything all together, we have an x equals 1, that's a one vertical asymptote, and x equals -4, that's another vertical asymptote that we solved for. We have a horizontal asymptote at y equals 1. And do I have any x-intercepts? No. The red graph is not crossing or touching this x-axis. Do I have a y-intercept? Yes, I do. Oh, I might have zoomed in too much. That y-intercept is at whatever we got. I think it was -9/4. So it's not a nice, pretty, like -2 or 0, -2 or 0, -3, nothing like that. It's a fraction, which is okay. It's still plotable. Unlike the imaginary numbers, Imaginary numbers I cannot plot on my graph. However, fractions, decimals, I can still plot on my graph. They're just not as nice looking, I guess. Okay, so I do have one y-intercept.